Hello everyone. The topic of this video is regularities of the Collatz conjecture. Those who are aware of the problem and familiar with the sets theory, can pause the video. You will understand everything from this slide. For the rest of you, let's proceed in order. Collatz conjecture is one of the unsolved problems in mathematics. The hypothesis is more than 90 years old and it became widely known due to the simplicity of its formulation. To explain the essence of the hypothesis, let's consider the following sequence of numbers, also called Syracuse sequence. We take any natural number n, and if it is even, then we divide it by 2, otherwise, if it's odd then we multiply it by 3 and add 1. Then we do the same for the resulting number and so on. For example, let's take the number 7, it's odd, and we multiply it by 3 and add 1, we get 22. 22 is even, we divide it by 2 and we get 11. 11 is odd, we multiply it by 3 and add 1, we get 34 and so on. As a result, the sequence reaches 1 and forms an infinite loop of numbers 4 to 1. The Collatz conjecture states that whatever the initial natural number n we take, sooner or later we will get 1. At the moment there is significant progress in proving the convergence of Syracuse sequence to 1. However, there is still no certainty in how quick or slow it happens. In this series of videos I will try to answer this question. Let's consider the Collatz conjecture in terms of set theory and define simple Collatz sets. Denote the class of given sets by the letter A. If the hypothesis is true, then any natural n corresponds to a finite set n formed from the elements of the Syracuse sequence. Sequence elements are added to the set n until we get a number that is already in the set n. This Python code is an example software implementation of building a simple Collatz sets for a given n. I will also give example of simple sets A formed from numbers from 1 to 7, indicating the cardinality datasets. The cardinality of the set is the number of elements in the set. Let's define base Collatz sets. Denote the data class sets by the letter B. Any natural n corresponds to a finite set Bn, which is the union of simple Collatz sets from 1 to n-1. As we can see from the definition, the set B1 will be the empty set. This Python code is an example software implementation of building a base Collatz sets for a given n. Also, I will give an example of a set B formed the number 8 being the union sets A with indices from 1 to 7, which were considered as an example earlier. From the base Collatz set, two subsets can be distinguished. Let E denote the subset of even numbers, let O denote the subset of odd numbers. As an example, let's take the set E8 and O8 forming the set B8. Let us define non-intersecting Collatz sets. Denote the class of these sets by the letter C. Any natural n corresponds to a finite set Cn, which is the difference between the sets n and Bn. That is, in set Cn will include all elements of the set n is not an incoming set of Bn. In fact, software code that generates set B above operates with non-intersecting sets based on this example of non-intersecting Collatz sets, based on this wording. I will give an example of non-intersecting Collatz sets formed from numbers from 1 to 7. Disjoint Collatz set with any even index always will either be empty or contain one element. Therefore, its cardinality will be equal to either 0 or 1, and taking into account the circumstance for analysis patterns, it makes sense to also highlight two subsets from the base set, B. Let's denote subset B with odd indices as B prime. And the subset of B with even indices we denote as B double prime. Inside these subsets, we also select subsets of even and odd numbers. So, all the main definitions are given. It remains to form test-based Collatz sets and analyze them for the presence of regularities in the generators their elements. Let's analyze the capacities of the base Collatz sets and its subsets constructed from all 16-bit numbers. Here and further, speaking of n-bit numbers, I mean numbers that need n bits to represent. Let us form the sets Bn and index range from 1 to 2 to the power of 16, and also calculate the cardinality of the corresponding sets, O, and E. I will give an example of two simple software implementations of source formation data for our analysis in Python. The algorithm that implements the first program illustrates well the logic of building a set B with a sequentially changing index. However, it is clearly not optimal from the point of view of speed. This algorithm has quadratic complexity, and the construction of base sets from all 20-bit numbers will take no longer minutes and hours, and for 34-bit numbers it will be months already. You can reduce the complexity of this algorithm to linear logarithmic using binary search tree, but here we need to consider that the main resource on which this problem comes down is not speed, but memory. And for storing information about those elements present in the set B when organizing a binary search tree, it requires 3 times more memory compared to a normal array. The second program implements bitmap storage algorithm to keep information about elements already present in the set B, and it has linear complexity. However, even at this implementation to build base sets collate from all 34-bit numbers in Python, it will take several days, and calculated data will contain a certain error associated with the outputs of some elements outside the allocated bitmap. As for the speed of execution, there is already a lot depends directly on the programming language. Translating the program into the machine code and use of the interpreter, which is Python, to form set B with index greater than 1 billion is not the best idea. In general, software implementation of this task is a separate issue. To get the necessary calculated data, I used C++ in conjunction with assembler, which with respect to Python gives a 1,000-fold gain in execution time. However, back to the results of preliminary data. As a result of the execution, this program generated a list with cardinalities values of sets O and E with indices from 1 to 2 to the power of 16. For dependency analysis, we will use pandas library, and first of all we will transform the resulting list of values in the data frame, after which we can evaluate the correlation between the cardinality sets, O, and E. Correlation data show that there is a clear relationship between cardinality of sets of even and odd elements of the base set. To determine its nature, let's represent this dependence graphically. The graph shows that the dependence is linear, and cardinalities of sets of even elements to odd tend to a constant. The constant to which the given relation tends is nothing but the root of 3. Small fluctuations at the beginning are easy understandable if you look at the process of formation of a sequence in the binary system. Nodal points are marked on the graph. They correspond to points with indices of the form 2 to the power of n. Anchor points are transition points with one index bit depth to another in binary number system. Obviously, in the intervals between the fluctuations will exist as nodal points, and the values at the node points themselves will contain already summary information about the influence of all patterns with the corresponding bit depth of the index. That's why, to build analytical dependencies, we will take information on nodal points. While we did not switch to analysis by key points, and we have a complete set of data on the cardinality of all base Collatz sets from 1 to 2 to the power of 16. Imagine base Collatz set in graphical form. Here are graphical representations of the base Collatz sets with index 2 to the power of 16 in natural order of its formation and sorting elements in ascending order. Also, for evaluation, the dynamics of changes in the base set are given graphs of set B with index 2 to the power of 15 and 2 to the power of 16. These graphs show that there is dependence of the cardinality of the set B in the nodal points from its index. Let's select node information from our data frame. Cardinality value of the set B at nodal points with increasing of n are almost doubled. It is clearly visible starting from n equals 8 already. At this stage, it is already clear that there are a number of dependencies of the cardinality of the base Collatz sets on the capacity of its index represented in the binary system. To confirm these dependencies, it is desirable to have a large sample of data. Test set relied on 65,000 base Collatz sets. As a working sample, we use a sample of 17 billion sets. To get a working sample, I used combined approach. It's a bitwise array in conjunction with a binary search tree, for elements that go beyond the selected bit array. As an implementation language, I used C++ in conjunction with assembler. Load pre-calculated data directly to the data frame, add calculated columns and group the necessary for analyzed data through pivot tables. The resulting data frame has almost 100% correlation. Let's derive some interesting dependencies, which can be formulated on the basis of this data frame, displaying them graphically. Latest 5 points of the graphs are presented in the table form to see what value seek appropriate dependencies. The blue color represents the dependency we have already considered. This is the dependence of cardinality sets of even numbers from odd numbers. The dependence of the Collatz base set cardinality ratios at adjacent nodal points is shown in green. Dependency of cardinality of the base Collatz set from the index is shown in red. Similar dependencies on the index constructed for the subsets O and E. The first two dependencies look promising in terms of analytical evidence, because the constants to which the dependencies tend have meaning in logic. To decipher the number to which the third dependence aspires, I will give one more graph. We see that our dependence can be divided into two, on the basis of the parity of the index. If we consider set B with odd indices, then this dependency strive for 2. Dependency set B with even indices tends to 1/6. I would like to pay attention to one more thing. Scale of all of the given graphs is a cardinality law, since n, displayed on the x-axis, is an indicator degrees for the base 2, so here on the interval n, from 1 to 10, the chart displays indices from 1 to 1024, and on the interval from 10 to 34 indexes from 1024 to 17 billion are displayed. If you build this graph on a regular scale, then you can see all the insignificance of the initial fluctuations. As a summary, in the form of hypotheses, I will describe the obtained numerical dependencies by formulas. Hypotheses give us, at a minimum, what bit depth of a number in the binary number system one can roughly determine the upper bound of the number steps for which the Syracuse sequence built from this number will come to 1. And also the maximum number above which the given sequence will not grow. How to get a rough estimate is quite obvious. We will talk later about how it can be clarified. In this video, I have presented only a part of the received dependencies. From my point of view, there are a few more interesting ones, and we will talk about them in the next videos. And now, thank you all for your attention, and see you soon.